morning, everybody. I welcome you all to my second lecture on the concept of series and parallel resonance. In my previous lecture, I have covered the introduction part regarding resonance and the various theoretical concepts related to series resonance. In today's lecture, we are going to see the various concepts pertaining to parallel resonance. So, in parallel resonance, these are the concepts that I am going to cover in today's lecture. The derivation for the expression of resonant frequency, characteristics of parallel resonance, the derivation for the expression of cutoff frequencies as well as bandwidth in parallel resonance, alternate expression for cutoff frequency, definition as well as derivation for the expression of quality factor in parallel resonance, alternate expressions for quality factor, and the derivation for the expression of resonant frequency of a tank circuit. So these are some of the possible combinations for parallel resonance circuit. So every possible combination will have its own expression for resonant frequency, cutoff frequencies, bandwidth as well as quality factor. In today's lecture, in our entire analysis of parallel resonance circuit, I'll consider the first combination, that is resistor, inductor, capacitor connected in parallel, excited by a current source. Now let us derive the expression for resonant frequency in parallel resonance, considering resistor, inductor, capacitor in parallel, excited by a current source. So like the series resonance, even in parallel resonance, the circuit will be pure resistive at resonance. The admittance of the given circuit Y is equal to 1 by R plus j omega C plus 1 by j omega L. So therefore Y can be written as 1 by R plus j into omega C minus 1 by omega L, where omega C is called capacitive susceptance and 1 by omega L is called inductive susceptance. So at resonance, the susceptance value becomes 0. So I'll be left with Y is equal to 1 by R. So therefore at resonance, since susceptance becomes 0, omega C minus 1 by omega L is equal to 0, which will give me the expression for resonant frequency to be omega R is equal to 1 by root LC. Thereby Fr will be nothing but 1 by 2 pi root LC. So therefore I can conclude that in parallel resonance circuit, the admittance is purely resistive, that is Y is equal to G, which is 1 by R. Since it is resistive circuit, voltage and current will be in phase, so the power factor also will be unity. The magnitude of admittance is minimum at resonance, which is equal to the value of conductance. So inductive susceptance. So the expression for inductive susceptance BL is equal to minus 1 by 2 pi Fc. So if I draw the graph between inductive susceptance and frequency, it is nothing but rectangular hyperbola, but starting from negative axis as shown in the graph. Similarly, capacitive susceptance BC is equal to 2 pi Fc. Since both are directly proportional, the graph between capacitive susceptance and frequency will be a straight line passing through origin. So in the characteristics of parallel resonance, we are going to see how your admittance response as well as current response varies with respect to frequency. So first we will see the admittance response. We all know for a parallel RLC circuit, admittance Y is nothing but 1 by R plus j omega C minus 1 by omega L, where omega C is nothing but BC and 1 by omega L is nothing but BL. So since we know that the inductive susceptance BL is inversely proportional to frequency, and capacitive susceptance BC is directly proportional to frequency. For lower frequencies, inductive susceptance BL will dominate with respect to capacitive susceptance BC. Therefore, at zero frequency, inductive susceptance BL value will be infinity, whereas the capacitive susceptance value BC will be 0. Now, when I vary my frequency from 0 to resonant frequency as indicated, since in this range inductive susceptance dominates over capacitive susceptance, with increase in frequency from 0 to resonant frequency, BL value will decrease, correspondingly admittance value will also decrease. Similarly, when I increase the frequency from resonant frequency till infinity, since in this range capacitive susceptance is dominating when compared to inductive susceptance, with increase in frequency the BC value will increase, correspondingly admittance value will also increase. So this is the admittance response with respect to frequency. Now coming to current response, we all know that I is equal to V by Z or V into Y. So here the current as well as admittance both are directly proportional. So therefore, for lower frequencies, as we have seen, with increase in frequency from 0 to resonant frequency, admittance is decreasing. Since current and admittance both are directly proportional, so here with increase in frequency, since the admittance is decreasing, correspondingly current also will decrease from 0 to resonant frequency since they are directly proportional. Similarly, for higher frequencies, as we have seen, with increase in frequency from resonant frequency till infinity, admittance increases. Since current and admittance both are directly proportional, correspondingly current also will increase. So this is the characteristics of parallel resonance. So the definition for cutoff frequency in parallel resonance. So in current response of a parallel RLC circuit, you can observe that the two frequencies, that is F1 as well as F2, the power is twice that of the maximum value and the current is root 2 times of its maximum value. Hence F1, that is lower cutoff frequency, and F2, that is higher cutoff frequency, we can define as the frequencies at which the power is twice the maximum value or the current is root 2 times the maximum value. So now let us derive the expression for cutoff frequency in case of parallel resonance. Considering the parallel RLC circuit excited by current response, the expressions for admittance as well as current can be written as shown. The power dissipated by this parallel RLC circuit can be written as P is equal to I square R or V square Y square by G. So when I substitute this expression for admittance in this relation, give me the power expression P to be nothing but V square by G into G square plus BC minus BL whole square. At resonance, we know that this expression becomes 0. So therefore, at parallel resonance, when that expression becomes 0, Y admittance will nothing but be equal to G. Therefore, power at resonance PR will be nothing but V square by R. So by definition, at cutoff frequencies, power will be equal to twice the power at resonance, P equal to 2PR. Substituting the expressions that we have got earlier, you get the following expression. So V square will get cancelled on both the sides. BC is nothing but omega C and BL is nothing but 1 by omega L. On simplification, I'll get the following expression. So after taking LCM, and rearranging the terms, I'll get a quadratic equation in omega. So this quadratic equation will have 4 roots, but I'll consider only 2 roots since frequency can never be negative. So out of 4 roots, only 2 roots will have positive values for omega. So in omega 1, omega 2 to be the roots of the quadratic equation, I'll get the following expressions for omega 1 and omega 2. Since we know that omega is 2 pi f, I'll get the corresponding expressions for f1 and f2. So these are the expressions for cutoff frequencies in radians per second as well as in hertz for parallel resonance. Definition of bandwidth. So bandwidth can be defined as the range of frequencies over which the power is greater than or equal to twice that of the maximum power. It can also be defined as the range of frequencies over which the current is greater than or equal to root 2 times its maximum value. And the other way, we can also define bandwidth as the difference between half power frequencies in series resonance and cutoff frequencies in parallel resonance. So bandwidth is nothing but omega 2 minus omega 1 or f2 minus f1. So now to derive the expression for bandwidth, so from the expressions of cutoff frequencies, we have the following expressions for omega 1, omega 2 as well as f1 and f2. So according to definition, when I subtract both the expressions, I'll get f2 minus f1 to be 1 by 2 pi rc and omega 2 minus omega 1 to be 1 by rc. So this is the expressions for bandwidth in hertz as well as radians per second. So from the current response, we can see that this range is indicated as bandwidth. So half of this portion is bandwidth by 2 and the other half is bandwidth by 2. So in terms of bandwidth by 2, omega 1 can be written as omega r minus bandwidth by 2. Omega 2 is equal to omega r plus bandwidth by 2. Similarly, f1 can be written as fr minus bandwidth by 2 and f2 can be written as fr plus bandwidth by 2. Substituting the expressions for bandwidth which you have seen now will give me an alternate expression of cutoff frequencies as shown. So let us derive the expression for quality factor. The definition remains same both in the series as well as parallel resonance. Q is equal to 2 pi into the peak energy stored by the energy dissipated in one period. Peak energy stored is half CVM square, where Vm is the maximum voltage. Energy dissipated in one period is I square R into T, where I is the RMS value of current and T is the time period. Thereby Q is equal to 2 pi into half CVM square divided by I square R into T. We know that RMS value is maximum value divided by root 2 and time period T is equal to 1 by F. So substituting these two relations in the expression of quality factor, which will give me the quality factor expression to be Q is equal to 2 pi into half CVM square divided by Im by root 2 whole square R into 1 by F. But we know that omega is equal to 2 pi F. From that 1 by F is equal to 2 pi by omega. Substituting this relation in the quality factor, so Q is equal to 2 pi into, instead of Im I have substituted Vm by R, and instead of 1 by F I have replaced that by 2 pi by omega. So on simplification, the expression for quality factor in case of parallel resonance will be omega R into RC. So the alternate expression for quality factor can be derived from the relation Q is equal to omega R into RC. We all know the expression for resonant frequency omega R to be 1 by root LC, from which omega R square can be written as 1 by LC, and from that relation capacitance C will be 1 by omega R square LC. Substituting this relation in the expression of quality factor, I'll get one alternate expression for quality factor, which is Q is equal to R by omega L. We all know that omega R is 1 by root LC. So substituting this relation also in the expression will give me another alternate expression for quality factor, which is Q is equal to R into root over C by V. So these are the alternate expressions for quality factor in case of parallel resonance. So tank circuit. So this is the tank circuit where the inductor as well as resistance are in series, which is in parallel with capacitance. So this is one of the parallel resonance circuit, and for this circuit let us derive now the expression for resonant frequency. So Z1 I'll consider to be R plus JXL, and Z2 I'll consider to be minus JXC. Since both are parallel, total admittance I can add as Y1 plus Y2, which is nothing but 1 by Z1 plus 1 by Z2. Substituting the expressions, I'll get the expression for both Y1 as well as Y2. Rationalizing both Y1 as well as Y2 and simplification will give me the expression for admittance, which is Y is equal to Y1 plus Y2, that is R minus JXL by R square plus XL square plus J divided by XC. Now separating real and imaginary terms from this expression, you will get the following expression for admittance. So at resonance, the imaginary term becomes 0. So equating the imaginary term to 0, I'll get the expression for the frequency, that is omega is equal to root over 1 by LC minus R square by L square. From this, the expression for resonant frequency FR is nothing but 1 by 2 pi into root over 1 by LC minus R square by L square. So this is the expression for resonant frequency for this tank circuit. So this concludes my today's lecture on the theoretical concepts of parallel resonance. In my next lecture, we are going to see some tutorials based on series resonance as well as parallel resonance. Thank you.